The mass flux from a 5 centimeter diameter naphthalene ball placed in stagnant air at 40 Celsius and atmospheric pressure is 1.47 times 10 to the minus 3 moles per meter second squared. So per second, sorry. So that is J, right? This is J. We're giving us J for stagnant air. Assume the vapor pressure of the naphthalene ball to be 0.15 atmospheres at 40 Celsius and negligible bulk concentration of naphthalene in air. So let's actually dwell on that sentence for a little while. What is that saying? Well, this is saying that, let me make a little room. Okay, you can be looking at this room from the side or from the top view. It's up to you, doesn't matter. And I'll place a little naphthalene ball just here. Okay, if you guys don't know what naphthalene balls are, those like white balls that people used to put in closets to keep moths away. They smell, they have a very characteristic smell. This guy has a diameter of 5 centimeters, and the vapor pressure of the ball is 0.15 atmospheres, and negligible bulk concentration elsewhere. So we have the naphthalene ball here in this corner, and the vapor pressure here is 0.15 atmospheres. And elsewhere, where we don't have the ball, we don't have any concentration. So over here, we only have air. We don't have any naphthalene, at least in the beginning. So therefore, the pressure vapor for naphthalene here is 0 atmosphere, right? There's no atmospheres there. There's 0 naphthalene anywhere else that is not the ball. All right. So the idea here is that we have a pressure gradient which can be translated once again into a concentration gradient. And what we would expect over time is that this little ball would release its molecules that would spread around this room, right? Just like a lump of sugar would spread its molecules in a glass of water if we leave it there. Now, what else do we need to know? Okay, so we haven't finished reading, right? If the air starts blowing across the surface of the naphthalene ball at 3 meters per second, so now we have air blowing across this at 3 meters per second. By what factor will the mass transfer rate increase? All other conditions remaining the same. So we would have a situation, a forced convection situation, when the 3 meters per second starts to blow on top of that, right? Because instead of relying on diffusion for the molecules to diffuse through air slowly and steadily throughout the whole room, if we have a molecule that has diffused already and now is airborne, that 3 meters per second over there is going to blow it maybe over here, right? So the molecule that would be here would otherwise be here with the 3 meters per second air blowing. So we go from a free convection situation into a forced convection situation. And the question is, how much more efficient, I think that's probably the best word, right? So much more efficient in transferring mass is the forced situation? So let's rewrite that. So we want to compare the two mass transfers. So we can compare J1 and J2. J1 being the free situation, free convection situation, so stagnant air situation, and J2 being the flowing air situation, right? So the forced convection situation, flowing air situation. Now, J1 has been given because they say in the beginning there, J1 is 1.47 times 10 to the minus 3 moles per seconds per meter square. So the question really is, what is J2? Because if I can find J2, then I can do, okay, the factor by which it increases is just dividing one by the other, right? And that will give us the factor that we're looking for. What was that increase? So it's just a matter of finding J2. If I can find J2, I can find the rate of increase. Okay, so what else are we given? We're given a correlation for Sherwood, which is great, and the viscosity and density of air, and also the gas constant, 82.06 centimeters cubed atmospheres moles Kelvin. So note that this is convenient, right? Because this is giving us an atmosphere, and we also have atmosphere for the pressure. So that's very convenient. What is not convenient is that centimeters cubed. So before I would do any maths on solving this problem, what I'll do is I'll actually convert that. I'll convert that R there. So R equals 82.06, and that is atmospheres centimeters cubed divided by mole Kelvin. And I want to convert that into meters, and I know that 100 centimeters is the same thing as 1 meter. And I can do that 3 times. So I'll eliminate the centimeters and do it to the meters. So that will be 82 times 10 to the minus 6 atmospheres meters cubed divided by moles Kelvin. Great, brilliant. All right, so what do we need to do? We need to find J2. If I can find J2, we can solve this problem. Easy peasy. So let me go ahead and do a little column here on the left, and I'll say this is the flowing air column. So everything that I do on this column here is related to flowing air. Okay. What do I need? I need to find J2. J2, remember the convective equation is just K2, K for mass, right, times the concentration. How can I find these things? Well, concentration I can find by relating the delta in pressure, right? I can use the delta pressure to find concentration. And K2, we know we can find K2 by finding Sherwood's number. And to find Sherwood's number, I need, where's my Sherwood's number? I need Reynolds and Schmidt's number. So I need Reynolds and I need Schmidt's number. Schmidt's and Reynolds probably. Schmidt's and Reynolds. Okay, so the game plan here is let's find delta C. Then let's find Reynolds, Schmidt's, and Sherwood. With Sherwood, we find K2. With K2, you find J2. With J2, you find the rate between the two of them. That's our game plan. All right, so let's start with the delta C. Well, delta C, like we did on the second problem today, the second question, we can also find by doing delta P RT, right? And delta P, in this case, we know what's the pressure gradient here because we have 0.15 atmospheres where we have the naphthalene ball and no atmospheres of the naphthalene ball elsewhere, right? Because when this first starts, we don't have any naphthalene in the room, just where the naphthalene ball is. And for the R, we have the 82.06 times 10 to the minus 6 meters cubed, atmospheres divided by moles Kelvin. And my temperature, I don't think I wrote down the temperature. 40 Celsius. So my temperature, let's put it down here. My temperature, this is taking place at, know how temperature became secondary, right? Temperature was always the main thing we needed first to be able to start. So this is 313 Kelvin. 313 Kelvin. Unit-wise, what happens? Atmospheres, kelvins. We're left with moles per meters cubed, which is brilliant because that is indeed a unit for concentration. So my driving force here is dependent on 5.84 moles per meter cubed, which is the different concentration that I have from where the naphthalene ball is to everywhere else in the room, right? And because there's that difference there, we'll have a mass transfer. Okay, good. What else? Now we need to find K. And to find K, we need Sherwood's number. And to find Sherwood's number, we need Schmidt's number and Reynolds. So Reynolds is density, velocity, diameter of the ball, characteristic length in this case, and viscosity. We were given all these things, right? We were given density. Where's my density? There it is. Density, viscosity, velocity is 3, and the diameter of the ball is 5. So we have everything good. So 1.123 kilograms per meters cubed. Velocity is 3 meters per second. Diameter of the ball is 5 centimeters, so 5 times 10 to the minus 2 meters. And viscosity is 1.8 times 10 to the minus 5. That gives me 9,358. And that's brilliant. So now let's find Schmidt's number. Schmidt's number is the viscosity, my density, and my diffusion coefficient, or diffusivity, which we don't have, right? Because this is, check it out, we have 1.8 times 10 to the minus 5. That is all good. We also have, let's divide here. We also have the density, or specific mass in this case, 1.123. But then we don't have the diffusion coefficient. Okay, and we can't really move forward without having that diffusion coefficient because we need that guy to be able to calculate Sherwood to be able to calculate K. Okay, so we're kind of stuck here. So we need to go back and actually think about this problem a bit more so we can solve it. Because remember that we talked about how for these two situations here, stagnant air and flowing air, for these two guys here, the K will be different, right? Because they have different dynamic conditions. One is stagnant, right? So free convection. The other one is forced convection. So because it's different, our Ks will be different. But they're both naphthalene diffusing into air under the same pressure gradient and under the same temperature, 40 Celsius. So their diffusivities are the same. That means that if I can find diffusivity using stagnant air, for which I have more information, then I can use that diffusivity on the flowing air and then solve it for flowing air and go ahead and do that. So I'm about to do exactly that, and that's why I separate that in flowing air over there, because now I'm going to do a little barrier here. And I'm going to start solving things for stagnant air. All right, let me just keep my barrier so that this is continuous. Okay, cool. So what do we need to do here for stagnant air? Well, what are we looking for? We're looking for the diff, right? The diffusion coefficient. How can we find diffusion coefficient? Well, there's a couple of ways. Let's actually list them down. I can use Schmidt's number because I know Schmidt's number is viscosity, density times diff. I can also use Sherwood's number because I know Sherwood's number is K. In this case, I'll use K1 instead of K mass, okay, just because to differentiate from K2. K1 characteristic length, which is diameter of the ball, divided by the. Okay, so on the first possibility, I don't have Schmidt's number, I don't have this. So I have two unknowns. Over here, I don't have this, I don't have this, and I don't have this. So I have three unknowns. So I can't really find Schmidt's number. There's only one equation for it. But for Sherwood number, I have more than one equation, right? I have the correlation as well. And the correlation says it's 2 plus 0.552 times Reynolds to the, what is it, 0.5? Yeah, 0.5 times Schmidt to the 0.33. All right, so note that here I also have Schmidt and Sherwood, so it's kind of a problem, right? There's just one little detail that we can use to our advantage. What's that detail? The detail is that on stagnant air, Reynolds is 0, right? And you actually have that tip given to you right in the beginning of the problem. Because if it's stagnant air, we don't have a velocity. If velocity goes to 0 on the Reynolds term, then Reynolds goes to 0. And if Reynolds goes to 0, this whole term goes to 0, and we're left with Sherwood number equals 2, right? It's 2 plus whatever that is. So Sherwood equals 2. If Sherwood equals 2, then that is something we can use to our advantage, because now we know that this guy equals K1 times the diameter divided by the thing we're looking for, diffusivity. So it's a matter of us finding K1 to be able to find diffusivity. And now I ask you guys, how do we find K1? Freeze. Good. So the game plan now is to find K1 using the convective relationship, right? And then that means that I can find K1 as long as I can do J1 over delta C. And luckily, I have these two things already. J1 has been given from the start, and that was 1.47, as you just told me. 1.47 times 10 to the minus 3, is it? Double check. I lost it. Minus 3, good. And that is in moles per meters squared per second. And our delta C, if you guys recall, is we got from the difference in pressure, and like that doesn't really matter whether we're just talking about stagnant or flowing, right? Because that is the difference in concentration that's going to make this happen on both situations there. 5.85 for 84. 5.84, and that is moles per meters cubed. So what happens with our units? We have moles and moles, and then we have meters cubed with meters squared. So we're going to have meters per second, which is exactly the units of K we're needing, right? So this turns out to be, what is our K? 2.517. Okay, so know how we're calculating K1 only because we couldn't move onwards with the flow in air situation, right? So we're doing all these things for the stagnant one just because we got stuck on the flow in air one. We wouldn't need to do this if we weren't stuck. And now we can find the diffusivity, right? Because the diffusion coefficient, continue on from this relationship here, the diffusion coefficient will be equal to K1 that we just found, 2.517 times 10 to the minus 4, multiplied by the diameter of the ball. It's 5 times 10 to the minus 2. And we're dividing everything by Sherwood's number, which happens to be 2. So the diffusion coefficient for this problem here is approximately 6.293 times 10 to the minus 6 meters squared per second. Okay, so we did this whole loop so that we can find this guy, and we know this guy applies for both, and that's the beauty of it, right? We know that this guy also applies to the flowing air condition too. So I can go ahead and plug in that number into where we have the question mark. So over here, I can remove this. I can plug in 6.293 times 10 to the minus 3. Oops, sorry, minus 6. And now we can solve for Schmidt's number, which was where we got stuck before. So Schmidt's number happens to be 2.547. Cool. So now we can go at, remember what we were doing, because it's been such a long time that we forgot, right? Our game plan was to find J2, and to find J2, we needed to find delta C that we did, and K2 that we didn't, because we needed Reynolds, that was good. Now we got Schmidt, so we need Sherwood so we can find K. That's the idea. We need Sherwood so we can find K. So let's go ahead and find Sherwood, which is the last piece of the puzzle. And Sherwood will be 2 plus 0.552. That multiplies Reynolds that we have over here, Reynolds, 9358, that's the 0.5. And Schmidt, which is 2.547, and that's to the 0.33. And that gives me a Sherwood number of 74.7. 74.7. Right? And now with Sherwood number, I can find K, which was the whole idea after all. What is K? Well, let's remember that Sherwood, let's do that like this. Sherwood is 47.7. And you know this has to be equal to K, in this case K for 2, times the characteristic length divided by the diffusivity or diffusion coefficients. So therefore, K2 equals 74.7 times the diffusion coefficient, which is 6.293 times 10 to the minus 6 divided by diameter of the ball. Okay, so that means that K2 equals 9.4 times 10 to the minus 3. 9.4 times 10 to the minus 3. That's meters per second. Okay, this is meters squared per second, and this is meters over here, so those guys can cancel each other out. Meters per second. All right, cool. So now we can finish off, right? There's two ways we can go about this. Let's do both just for the sake of it, but the first way I think is more intuitive. This one. I want to find J2. That's what I've been looking for this whole time, J2. And I know J2 is just K2 times the delta C. And I have both things now, so I can do 9.4 times 10 to the minus 3. That multiplies 5.84. Okay, I'll have, this is meters per second, moles per meters cubed. So my J2 equals 5.49 times 10 to the minus 2 moles per seconds meter squared. And I can finish it off because remember the question itself, how much more efficient, right? That's what we were trying to find out. How much more efficient was this guy in relationship to the stagnant one? And to do that, we can do, you guys can go away. We can do 5.49 times 10 to the minus 2. You can have a little peek to see if it's indeed more efficient. This is 1.47 times 10 to the minus 3. So yeah, about almost an order of magnitude higher. They have the same unit, both of them, so this will be just a ratio, right? And that turns out to be 37.3. That will be our answer right there. Okay, so it's about 37-fold more efficient. The mass transfer happens 37-fold more efficient on when we have that 3 meters per second wind blowing on the naphthalene ball in relationship to if we don't have that. What is the other way we could go about this? Well, we can notice the following thing that would happen. J1 over J2, that will be K2 times delta C divided by K1 over delta C, right? Since we're talking about the same concentration in both, these guys go away. So what we could do is instead of them, we could just do the ratio between the two Ks. That's another way to go about it, because we have those two things, right? We have K2, which is 9.4 times 10 to the minus 3 meters per second. And we have K1, which is 2.517 times 10 to the minus 4 meters per second. So that's going to render the same result. Okay, so you could have done that too. It's another option. I think this one, the first one, is more intuitive because we were after J2 the whole time. So up to you. Questions on this problem?